Hi, I'm Sibi Venkatesan from UC Berkeley, and I'll be talking to you about how we use non-rigid registration to teach a robot how to suture from human demonstrations. Suturing is a time-consuming and repetitive task, as you can see in this video. Since we work with deformable objects like skin and flesh, the variability in shape and structure of the tissue makes this especially challenging. But a fast and robust autonomous procedure would go a long way in reducing surgeon fatigue and shortening operation times. There's been a lot of work in similar spirit in the past where surgical subtasks have been automated using robotic instruments and such. More closely related to our work, there's been research done on automating surgical suturing, firstly using motion planning or other hardwired approaches, or leveraging human demonstrations to tie surgical knots. The main difference between our work here and the ones mentioned below is that we explicitly use the geometry of our workspace, say a point cloud of our setup, while they break down and analyze the trajectory generated from the human demonstrations. Now let's look at a more concrete scenario of suturing with a robot. This is a simulated setup of the Raven surgical robot as developed in UC Santa Cruz and University of Washington. The image on the right is the setup we're working with. Our task is to teach this robot how to perform suturing from human demonstrations. So here's my colleague recording a demonstration and simulation. Let me walk you through this. Our task here is to first pierce the flap on the right, and then pierce the flap on the left, and then loop over the suturing thread twice, as you'll see in just a moment. And then tighten to get a surgical knot. So far, we have a human demonstration for a particular initial configuration, and the robot is presented with a new configuration, say the image on the right. What does it do here? Essentially, we want to generalize our demonstrated trajectory so that the robot may perform it for a new configuration. Let's look at a cartoon example to make this clear. This is, say, a point cloud of our training situation. It has 4 points here, but it can have how many other points you'd like. And this is our demonstrated trajectory, which is adapted to this particular point cloud. Now the robot is presented with a new point cloud with the points moved around a little bit. What does it do here? Here we use a technique known as non-rigid registration, which has been explored in the past, especially in medical imaging. So we use non-rigid registration to register the points onto each other from the training situation to the test situation. The novelty of our scheme here is that after doing this, we treat these registered pairs of points as samples of a function that maps from R2 to R2, or from R3 to R3 in general, and then we essentially machine learn this function to warp the trajectory from our demonstration to the new situation. Now what is this in terms of math? First, we want to respect our registration so that the function matches up the points correctly. But there are an infinite number of functions which satisfy this constraint. Now we want a reasonable function out of all these available functions, and a reasonable choice is one which minimizes this objective. This expression is basically the norm squared of the second derivative of our function, summed over all of space. Now we notice a few things here. If that objective goes to 0, we're left with an affine function. This means translations, rotations, and scalings can be encoded for free. Secondly, as we'll see in just a moment, even though we're searching through an infinite set of functions, we can solve this efficiently by just some matrix manipulation. This formulation has an optimal solution corresponding to the thin plate spline model. This has been explored in many areas of computer science, particularly computer vision and graphics. Now the optimal solution takes on the form as shown below. A sum of radial basis functions centered around the training points plus an affine component. Once we know that the optimal solution is going to be of this form, finding it is just pretty much a least squares problem. So far, with this function we've just learned, we've transferred over our gripper trajectory to the new situation. Now we need to execute this gripper trajectory on the robot, and for this we need to motion plan. And here's what we use. Trajectory optimization was proposed by Shulman et al. And IROS this year. It solves an essentially non-convex problem, non-convex because of the collision constraints, by repeatedly solving local convex approximations of the same. This technique solves a large fraction of motion planning problems in complex environment with obstacles. I urge you to read their paper if you want to know more. This completes our pipeline for transferring trajectories from human demonstrations. In order to validate our approach, we conducted several experiments in simulation. We kept one side of the flap stationary, and we perturbed the other side by x translations, y translations, z translations, x rotations, y rotations, and z rotations, and combinations and scalings of the same. Now here is a video for a particular perturbed configuration. The green grid is a visualization of the warping from the training to the test situation. We divided the task into several segments and warped the space at the beginning of each of these segments. Why do we break it up into segments? As we execute the task, the configuration of our setup changes. So we rewarp each time it is critical to know what the current configuration looks like in order to execute the next portion of the task. As you will see, once we run the entire pipeline, the ravens perform successfully in this particular situation. Here are a few numbers and plots from our experiments and simulation. Consider this plot. It has as its horizontal axis the warping cost, which is a measure of how distorted the new setup is. In fact, it's exactly the objective which we minimized earlier. And the vertical axis is the probability of success. We see that when the warping cost is low, our setup is very similar to the initial configuration and the rate of success is high. As the configuration gets more and more distorted, the warping cost increases and the performance deteriorates. Here are two more plots with maximum position error and maximum orientation error on the horizontal axis. The vertical axis remains the same. Let me define these errors for you. First, you warp the demonstration to get a gripper trajectory. Then you optimize the trajectory to execute this on the robot. The maximum error over all time steps between the warp trajectory and the optimized trajectory are what you see here. These plots show the same trend. When the errors are low, the performance rate is high, and when these errors become larger and larger, the algorithm sees more failures. For example, for the maximum position error, we have a 90% success rate with maximum position error of 4 millimeters or less. And for maximum orientation error, we have a 90% success rate when the orientation error is less than 0.6 radians. Now, as a proof of concept, we conducted experiments on a real robot, the PR2. The PR2 is very accurate kinematics, and we factored out the perception problem, as I'll talk about in a little bit. The image on the right shows the setup we worked with. Here's a video of a demonstration on the PR2. The task is broken up into segments, just like simulation, and here we use a joystick to mark the start and end of the different segments. The task here consists of piercing the first flap, followed by piercing the second flap from the inside, and then removing the needle. Now, the difference between these experiments and simulation is that before, we had full state information. Here, in order to account for that, we factor out the perception problem by having a human in the loop annotate the segments with the help of visual aids, as you can see the black marking along the cut and red dots for the points along the cut. Thus, with this, we know the correspondences of the points beforehand. Again, we performed several experiments in the PR2, mainly using rigid transformations like rotations along the X, Y, and Z axis, non-rigid transformations like bends along and across the cut, and stretches, where we used a diagonal pair of holes so that we can increase the distance between the holes. Now, this is a video for an experimental run for a rotation of 15 degrees along the Z-axis. Now I'll talk about a few extensions which could potentially improve our algorithm. First, we want to use real-time tracking, as you can see in the video on the left. With this, we could track both the non-rigid tissue and the key points in the scene over the different segments so we know where they are. Secondly, we could potentially jointly optimize for warping and trajectory. Say we found a great warping, but the corresponding trajectory was deep in self-collision, and executing it resulted in a failure. But maybe there was a warping which is close, but not as close as the optimal one we could have found. But the corresponding trajectory was much easier to execute and therefore resulted in a success. So maybe jointly optimizing could potentially solve a lot of the failures which we might have otherwise experienced. Finally, we plan to implement this in a real surgical robot. The challenges here are perception at a small scale and working in a constrained and uncertain environment. To wrap this up, we present an approach using non-rigid registration to transfer trajectories from human demonstrations to new configurations. We validated this approach for a simplified suturing scenario on both the simulated Ravens and the PR2, and we were successful under varied initial conditions. Finally, here's a link to our website where you can find more information, and also here's a link to the code base where you can find general code for learning from demonstrations, not just for suturing. Thank you.